After coming across a very exciting equations that meets all of our conditions, one might ask, what is so special about this number 2? Can you use other numbers, say 3, 5, 17? And you might say, okay, let's try it. So if instead of using 2 as the base, we use 5, well, it is true that the curve shifts a little bit, but it still meets all our conditions. So you can use any other number that you want as long as it's positive. Now, what is the best number to use here, knowing that all the numbers could work? As you've guessed, the number that most mathematicians like is the Euler's number, which equals 2.718. And why we really like to use E instead of other bases, because it's much easier to work with. Say you know what the value of 5 to the x is, you want to know what x is. On your calculator, you have to calculate the log of 5 to the x base 5, which you probably don't have on your calculator, but you all have natural logs on your calculator, so it's much easier to go with E instead of 5 or 2 or 17. So now that we know that out of all those numbers that we can use, we're using E, we can just forget about these 2 and 5 and then continue working with the equation e to the x divided by 1 plus e to the x. Now, this is very specific equation. What if we want to generalize this equation? So the first step would be to add a coefficient to e to the x and just add some flexibility to the equation and then play with the c. As you can see, all of these values of c meet our conditions for a smooth S-shaped curve between y equals 0 and y equals 1, but it has to be restricted to positive c's, because if this was not restricted to positive c's and if you use a negative number for c, the curve would fall apart. So the second step to generalize this equation would be to raise this e to the x to some arbitrary power, let's call it c2. And here you have the more generalized version of the same equation that we had before. So let's try this one. If you write your equation in this form, then again you can play with the c1 and the c2. If you play with c2, what happens? As you can see, you can change the slope, how fast it goes up or goes down, and you can reverse your S-shaped curve. You can make it go up or go down or be flat. And what happens if you play with C1, as we saw before, you can shift it to the left, you can shift it to the right, but it cannot be negative number. So the next step would be to rewrite the generalized equation we have built into a more useful format which looks nicer and is easier to interpret. What we need now is to remember some pre-calculus equations. So as a reminder, you remember that exponents and logs are inverse functions. So if you raise e to the power log of c1, this exponent and log would cancel out and you will be left with c1. And you remember that raising e to the x to c2 would be equal to raising e to the power of c2 times x. So equipped with these formulas, we can now rewrite our equation. We can go back to our equation and then bring down this c2 as a multiplier or as a coefficient of x and bring up this c1 to the power, but we know that we cannot use c1, we have to use log of c1, and then rewrite this equation in a new, better looking format. And just to show you that these two are the same equations, I'm going to click on both of them and then just play with these numbers and then show you that the purple curve is exactly the same as the black curve. As you can see, we haven't changed a thing. They're exactly the same. This function and this function, they're exactly the same. So now let's look at this generalized and better looking equation we found. What is the C2? Well, remember, it was just an arbitrary constant we came across. So we just chose the name C2 for this constant. We can choose any name we want. And what about the C1? Well, C1 was another arbitrary constant, so log of C1 is another arbitrary constant. So why call it log of C1? We can call it anything else we want. And so we can rewrite this equation now using the more common terminology. So instead of C2 times X, we can just call it beta 1 or B1. And then instead of log of C1, which is an arbitrary constant, we use another arbitrary constant. We call it beta 0 or B0. And then again, these two are the same, but because we're using different C1s and C2s than B1s and B0s, that's why they don't look the same, but they're exactly equivalent. Now, let's play with these numbers B0 and B1. What happens if I change this B1? So if I increase B1, I'm increasing my slope. If I decrease it and use some negative numbers, I've reversed my S-shaped curve. It goes down, it's decreasing, so this is nice. And what happens if it equals 0? My line becomes a flat line with no slope. Slope equals 0. Now, if I use, let's say, for example, beta 1 of 1 and then play with beta 0, what happens is that, as you can see, let's zoom out a little bit. What happens is that by changing beta 0, I'm shifting my curve to the right or to the left. And by changing beta 1, I'm changing my slope. So armed with these 2 degrees of freedom, I can make any S-shaped curve that I want, and I can approximate any S-shaped curve. Let's say, for example, this probability function that I have here. Let's try and see if we can fit this black lines on this red dotted line. So first of all, do you think beta 1 is positive or negative for this curve? So it looks like it's positive. So is it steep enough? Maybe a little more, maybe a little more. Okay, so now we have to bring it to the left. So let's to the right, sorry. So we'll bring it to the right. Is that enough? So how about 10.5? No. How about 9.5? Perfect. Well, it's not perfect, but it's very, very close. So armed with these 2 degrees of freedom, because we generalized our equation, we found out by playing with these 2 numbers, beta 1 and beta 0, we can fit any curve, S-shaped curve between 0 and 1 that we want. And that's what we did. So this is actually very, very close to the outcome of a logistic regression performed on these numbers. So if you input these blue dots that we started our analysis with to a logistic regression model, the outcome would be in the form of beta 0 and beta 1. And they would probably equal 5, something very close to 5.8, and beta 0 is very close to minus 9.5.